organizing members of the MaCFP Working Group. And this is just a quick overview of the guidelines that we shared this week for the experiments and modeling work that we'd like to organize in the next year and a half in preparation for the June 26th MaCFP-4 workshop. Right. So big picture, we'll do an overview of where we came from, and then Sima Hostika and I will present the condensed phase and radiation heat transfer subgroups exercises that we're going to look at for the MaCFP-4 workshop. And one more reminder for a few more of you who have joined us, we are recording this. That's great for those who have missed the meeting, but just please be mindful of that recording. So big picture on MaCFP, and we're about 10 years into that effort. I want to highlight how important it is that this is a collegial and cooperative effort between people around the world, whether they're experimentalists or modelers, and that's a special thing and a challenging thing to keep going. So it's all volunteer. Thank you for being here, and hopefully we can continue to expand on that framework so we can make serious and systematic progress together. All of the target experiments that we're looking at, they are built in this systematic way. So we identify a series of core fire phenomena that we believe are most important to advancing fire modeling, and we select experiments that are carefully controlled and set up and well documented that address these fire dynamics phenomena in a systematic way, from basic to more complex, kind of as a building block approach. So we've had multiple in-person and virtual workshops in the last 10 years. The proceedings for MaCFP 1 and 2 are now available. If you are following the GitHub repo, then you would have seen a notification about a month ago for the second proceedings document. We have a preliminary summary of experimental data on the solid phase at MaCFP 2, and proceedings for the third workshop are in a final draft stage, and committee members are just adding comments and fixing last things there. So this is a good body of work. We hope to share it for public comment. And I think as we look at these different building blocks, we should address how those are selected, because this is an important bit of feedback that we got from MaCFP-3, and we'd like to keep going moving forward. All of our cases look at addressing key phenomena in either the condensed gas or radiation parts of the problem, or these coupled cases. When you look at a case study on buoyant plumes or pool fires or wall flame spread or solid fire modeling, we hope they each address one of the or multiple of these key phenomena. And so as a group, we are developing this database of experimental measurements and corresponding model or numerical simulations of these results. It is a big effort to be able to compare between these data sets, so having the formatting there is important. And through this exercise, working together, we can identify what are we good at, what's challenging, what more do we need to study. So again, thank you all for being here. A big part of this effort is that network and being able to come together in a cooperative way. So holding this all together is the GitHub repository, and I'll encourage any of you who are not currently following that or watching that or starring that to please head on over to this link to do so. There are 3 subpages there for the gas phase, condensed phase, and radiation subgroups, and they each contain experimental data and modeling results looking at our core cases we just identified before. This is where you can go for all up-to-date data, measurements, property sets, simulation results, README files describing everything that's in there and how to make sense of that. And as you participate in this effort, we really want to move forward to submitting our data here in GitHub rather than just emailing it back and forth. That's a huge help administratively in that effort. We've learned through the last 10 years of MaCFP and from previous databases and previous efforts like this that having good metadata is important, having standard formatting is important, and all of this takes quite a bit of work. So if there are participants or you have colleagues who are interested in helping the effort and can volunteer time for that maintenance and analysis and scripting, we would of course welcome that help. So finally, we have a virtual discussion forum, and that link is here. It's also coupled through our GitHub page. If you have questions on specific cases or suggestions on where you want to go, or I just got an email earlier saying, I'm a modeler, I would really like to have this kind of data to help with this or that analysis, please post that here, and as a community, hopefully we can address these things. All right, so we're finally here for our tentative timeline. That was just a background on MaCFP. Now we can look forward on where we want to go. And we are in the 2025 year. This is somewhat tentative, so there may be shifts, but in the last month, we've shared our proceedings for MaCFP-2 and prepared final drafts for MaCFP-3 proceedings. And today we're going to go through our guidelines for how to participate in MaCFP-4, what are the cases there in the condensed and radiation phases. Through spring and summer of this year, on the condensed phase side, we hope that we can work with you to share material samples, run experiments that you would use for pyrolysis model calibration. And I believe SEMO will share in August a deadline or proposed deadline for some radiation work. If we get that by the end of the year, that would be great. And that moves us into next year. We have a first virtual meeting to highlight these results after some analysis and prepare our final modeling results in preparation for the June 26 MaCFP workshop. So that's our big picture. We are right here, just working on our guidelines of what these new cases are. I will now give an overview of the solid phase side of things, how we got to where we are, and the target cases we're going, and then SEMO can take over from me for radiation. This group was started in 2016, and the goal was to enable significant progress and a common framework for the selection of the experiments and modeling approaches that we need to develop better pyrolysis modeling. And so to do that, we need a standard way of sharing this data and interpreting that. We want to understand variability in the experimental measurements and the model calibration techniques and the results and how that propagates into real predictions of burning rate and fire growth. We are mindful that there's not necessarily one best approach here. We really do want to see what is the state of the art between different members of our community. So we encourage different experimental data, different calibration techniques. We don't necessarily say this is the best one, much less this is the best one for all different types of materials. But a huge part of this effort is learning where the field is at and how we can do better work together. So if we look at the first material we chose in this framework, we wanted something that was relatively simple, didn't have complex behaviors such as melting, dripping, flowing, charring, delamination. And naturally, that was a cast black polymethyl methacrylate, or PMMA. We kind of call that our MaCFP PMMA. And so going back maybe 6-7 years ago, we shared samples of this around the world. Roughly 20 labs in a dozen countries shared experiments in 8 or 9 different apparatus, conducted in 35 different test configurations and environments. So we had milligram scale tests, we had bench scale experiments, and started to see, oh, well, we're pretty good at our TJ experiments, but getting good DSC data is a challenge. Variability there, really sensitive instruments, so we're calibrating in the same way. We could see differences between different bench scale tests, like our FPA, cone, or gasification apparatus. And kind of surprisingly, when we looked at our cone data, individual labs results were fairly repeatable, but reproducibility between different groups was a little more limited than we expect. Some of that is differences in boundary conditions. Some of that was possibly not capturing exactly how we calibrated or set things up very well. So a lot to be learned just on the experimental side here, and it was very valuable, if challenging, to go through 20 different groups of data and how we submitted that. From all that data came property calibration, and so some groups did both. Some modelers were just able to pull from the cache of experimental measurements and develop their reaction mechanisms and associated kinetics and thermodynamics, or their heat transfer properties. And so we had a dozen or so different sets of those properties. And in MaCFP-2, all of that was used to predict these standard 0D and 1D thermal decomposition or gasification cases. And we could start exploring how do these variations in property sets, how do these variations in measurement data influence the real predictions that we care about, such as onset time to mass loss, the decomposition temperature, peak burning rate, and so on. And a learning outcome here was that the scatter in our model predictions was greater than our experimental variations. And we were only doing model-to-model comparisons. So while we couldn't say, well, this one is definitely right or wrong, they couldn't all be right given this scatter. So coming from MaCFP-2, we looked forward to last year's meeting in MaCFP-3 and developed a bench scale validation case. to allow our different modelers to compare their property sets to say, well, this or that property is off because of this calibration approach or this data set that we compared to. And then we could quantify by different metrics of heat transfer or burning rate, which of these models showed closest agreement to that validation data set. And then the real important impact now is we have a property set that we believe is fairly reasonable. Can we apply that to different flame spread cases? Let me actually pause for a moment just on this side and acknowledge Jason Floyd, who ran a lot of sensitivity analyses to look at how differences in the submitted property sets impacts gasification results, and then Morgan Bruns, who's working on a deeper analysis of that now too. So lots of people have contributed in the last year or so. They've added a whole bigger analysis there. These properties then now look at real flame spread. We had two cases, a corner wall environment that was similar to the SBI, and this was run by the University of Maryland group, and a parallel panel case that was based on the FM4910 test, and that was run here at NIST. And so if we look at this whole big picture, we now have measurement data from 20 different groups that was used to inform our model development by another dozen groups, and then we propagate that all the way through from measurements to properties to real prediction of burning rate and flame spread in cases that we believe are important. And we can start looking at what are our sensitivities to different properties or different boundary conditions that we apply. Do we have correlation between different scales? And this is written up in our MaCFP-2 and MaCFP-3 proceedings. So here's our whole framework from properties to real predictions of spread. What matters, what correlates, and how can we do that better? The feedback we had at the end of MaCFP-3 was a majority of our participants asked to look at addition materials, look at more complex materials, and specifically look at charring and charring materials. So this year, we'd like to focus on our MaCFP wood, which is a pine wood, and catalog, once again, what are the state-of-the-art approaches that we have to develop pyrolysis models for such materials? What's the variability in our experiments? Can we compare these property sets and these model predictions? And then eventually, can we validate which of these property sets gives us good agreement with the validation data set? And many groups may submit TGA, DSC, MCC, or cone, or different types of experiments. We are not saying that you must run any of these tests. We would like to see how the field likes to run these experiments, what they feel are important. But in our guidelines document, we do ask that if you run specific experiments like these, you follow the templates and test conditions and repeat them at least under one consistent set of environments or heating rates and so on. So please run whatever experiments you want. But if you are running cone and DSC, if you could repeat those under the conditions that we could all compare directly to, that would be great. So we have this wood. We will start this year by just looking at anaerobic pyrolysis model development. So it's still a big step up in complexity to understand that char formation and how that affects heat transfer and mass transfer through the degrading solid. We have found a supplier, and we're working with that as new, as the climate changes in terms of how we can buy things and how tariffs affects what's available. But we are set to buy dozens and dozens of these large planks of wood and then cut them or grind them to scale as we need to make little cone-sized samples, or if you're doing gasification experiments, make those circular discs for those tests. Just for the sake of model parameterization and seeing how variations in properties affect your simulations, we're also going to buy 4x4 versions of these materials to cut simple squares across the grain or cut them along with the grain, so we can see how thermophysical properties vary there and how that affects our results. All of these materials will be bought at the same time from the same supplier, from the same source. We'll prepare them in similar ways so that we're working with the same material for property development up to larger validation tests. So here's our core wood. It's a pine wood. We selected it because of its generally widespread use in furnishing and constructions and standard fire testing like crib fires. And again, please run whatever test you would like to for your property calibration. But if you're doing certain ones, we propose some steps in the guidelines for direct comparison. These are our properties that we're interested in, pretty similar as we had before. something on our reaction mechanisms, associated kinetics and thermodynamics, and then our transfer properties for heat and mass flow and interaction with radiation. We are requesting first just comparison of idealized heating scenarios. So a 0D TGA-DSC-like scenario to compare our property sets under controlled heating, and a 1D gasification scenario with different sample thicknesses and different incident heat fluxes, just purely as model-to-model comparison to see how differences in selected experimental data or calibrated material properties propagate into these results. That'll be our big goal for MaCFP-4. As we move forward to MaCFP-5, we can advance in complexity, look at oxidative pyrolysis, recognizing that the char that's formed can oxidize, produce different ashes and solid residue that releases more heat, and we may need to capture that with more detailed models. So as you run your experiments and develop your models now for that first step of an anaerobic pyrolysis model, please keep in mind that we are moving towards oxidation in future workshops, and we have in mind different larger validation cases, such as crit fires to look at burning rate with different porosity and crit size, and different modified wall fires with well-controlled boundary conditions that we can vary to change oxygen availability, re-radiation to that wall, and include some measurements of the controlling mechanisms there. So here's our wood. If you're interested in joining this experimental part of the exercise, please contact me directly at the email that you see here, or my colleague Mark DePinnon over at UL, who's been helping with the procurement and preparation of these wood samples. Send us an email, say what types of tests you can commit to performing in the next year, and this spring we can share inch thick or 25 millimeter thick slabs of these materials cut for cone or gasification experiments. We'll share powdered samples for TGA, DSC, etc. And we're happy if you can join us there. I will leave it up to Simo if he would like to continue directly or if we should pause for questions, but we'll switch from condensed phase to radiation phase, and I can stop talking for a moment.
Okay, thank you, Isaac. So shall I continue, or we have questions now?
No questions in the chat, and I don't see hands going up just yet, so maybe continue, and then we'll wrap up with questions from there.
Okay, good. Yes, so hello everyone. My name is Simo Hostikka. I come from Aalto University in Finland, and this radiation heat transfer subgroup was introduced in the last symposium in Tsukuba, and ever since we have, with a group of researchers who have kind of registered or told they are interested in this topic, we have met about once a month to take this activity forward. I think my co-chair Fabian Brandström is here in the meeting as well. So the radiation subgroup activity and MaCFP-4 consists of 3 phases. First phase includes benchmark data generation, and this activity was actually pretty much finalized last year. The results have been reported in the Journal of Quantitative Spectrometry and Radiative Transfer. And unlike the gas phase and condensed phase subgroups, our benchmark data is not actually measurement, but it's synthetic data, something that we calculate. So this data means photon Monte Carlo line by line calculations. And this data has already been made available in the GitHub repository of radiation group. The second phase, something we anticipated to do in the Tsukuba presentation, is the, no, please stay on this here. So this will contain simulations where we want to minimize the scalar field uncertainty. So basically, we take snapshots, frozen situations of a fire, and do radiation calculations without considering any fluid dynamics or anything. We take everything as granted. At the moment, we have participants at least from Aalto, Wuppertal doing, but we recognize that this activity is quite demanding, and target participants here are actually those who do radiation model development or somehow very devoted for the details of the radiation modeling. And therefore, during the last months, we decided to extend the exercise a little bit to phase 3, which means simulations with transient CFD. That is typical fire CFD calculations, but now it means that we will include some scalar field uncertainty. Target participants for this phase 3 are now basically all fire modelers who are interested in radiation. Now, next slide. Okay, here I just want to give you an example of what this benchmark data looks like. So we have taken the gas phase CFD predictions from the, I think was MaCFP-1 or MaCFP-2, and somehow the most reliable, best calculations for 2 of the test cases, methanol pool fire and ethylene flame, one computed using OpenFOAM, one computed using FDS. And from these simulations, we have stored few tens of snapshots, frozen scalar fields. And now the radiation modelers, Somes Roy and Sandon Powell, took these fields and calculated photon Monte Carlo line-by-line calculations, which to us now represent perfect data, perfect radiation calculation, which we will use as a benchmark data. Okay, next one. Here we have an example of what phase 2 calculations might look like. Surus Rashidzadev from Aalto has been using this benchmark data for to investigate the performance of different radiation models while he is developing a non-gray radiation model to be implemented in FDS. And this, as you understand, this is quite detailed work. It requires a little bit of work from the modeler to learn how to import the snapshots into a code and how to do the frozen field calculation and then export. So we are happy if we will have more participants doing this type of work. And of course, these data could be used by any radiation modeler using any CFD code other than FDS and OpenFOAM if you just implement the necessary data transfer features. Okay, next one. Phase 3, here we hope to have more participants from the fire community. At the moment, the idea is that we provide the original FDS and OpenFOAM input files that were used for those very original CFD calculations. And the users would take these input files and then do modifications to the radiation, possibly combustion, soot modeling parts, which influence radiation calculations, but nothing else. And then they can study the influence of the parameters, options, how to get correspondence with PMC line by line. And then they will report the requested output quantities to GitHub, as we have been doing in MaCFP rounds for the gas phase and the condensed phase. And here I have a list of output quantities we expect to ask from the users. I'm not going to go to any details over here. And the last part of radiative heat transfer here is what we hope to do to support the work of the condensed phase group. Over the years, we have noticed that some researchers have measured the spectral properties of solid fuel surfaces, reflectance, emissivity, and so on. And because this is closely connected to the condensed phase process modeling, heat transfer modeling, we hope to be able to provide guidance on how such measurements should be done so that they can be used in the condensed phase modeling, and also now to collect some database of the pine wood spectra. So we are looking at how different techniques, how to measure specular or diffuse quantities over which wavelength, using which kind of equipment, and how to interpret the data. And current idea is that we should be able to provide recommendations in August of this year. And the figure over here is just as an example how we started to look at, for example, if we take data from two sources, here two groups, one in our university, Arne Hovi, and then Gilles Parent from the University of Lorraine, they had measured pine needles, different pine species, different wavelength range, different equipment, but still we see that these data basically perfectly overlap over the wavelength range where the equipment's range overlaps. And this is something we would like to obtain. How to do that for the pine, hopefully we can help the condensed phase group over here. That's all.
Alrighty, thank you, Simo. All right, so we will wrap up with a quick summary of our cases and then who to contact if you have questions, and then we're open to questions for everyone here. A quick reminder for those who joined us a few minutes after we started, we are recording this meeting, so please just be mindful of what we share there. Don't share confidential information or anything like that. But hopefully we can share these questions and feedback with everyone who could not attend the meeting. And so we have presented the condensed phase subgroup and the radiation heat transfer subgroup cases that we'd like to look at from MaCFP-4. These have been written up in the guidelines document that hopefully you received by email. If you haven't, please send an email. We can get you on that mailing list. And in the condensed phase side, we are following the example that we started from MaCFP-2 and 3 to develop pyrolysis models for a simple material. Now we're going to apply that to a charring pine wood. And we are asking experimentalists this summer to perform experiments that they believe are useful for pyrolysis model calibration, submit that data to the GitHub repo, and share that so that modelers can then come in at the end of the year and develop material property sets using that data and perform simulations of idealized 0D and 1D heating scenarios. We're happy to have the support of the radiation subgroup to help with the characterization of absorption and emissivity properties of this pine wood. And then that subgroup is also organizing the more detailed radiation modeling exercise that Simo just presented. On the gas phase side, we do have 3 target cases. We don't have full details and the repo is not ready quite yet, but it appears they will be looking at soot formation and oxidation and how that affects thermal radiation transport in gaseous burner, the FM burner. We'll extend the MaCFP-3 flame spread cases to look at how submodel decisions affect things in a more constrained, systematic way. And hopefully there's a new target case for compartment and facade fires looking at flame structure and heat transfer. Those are the big target cases. We've gone through a lot of detail on the condensed phase and radiation side. And if you have general questions or further questions on specific things, please reach out directly to any of us here. But for now, I'm going to hope that we can turn this over to our participants who have questions or follow-up or feedback. And we have some time to answer that. And there are several other committee members, both on solid and radiation side, and I believe radiation gas phase too. Many of them are more knowledgeable than me, and hopefully they can help field questions as you have them too. You can unmute yourself, you can raise a hand, you can type something in the chat.
So, Isaac, real quick, can you go back to the properties list for the condensed phase?
All right, what's up?
So, I'm thinking I mean, it's a good list. I'm just thinking that, like, for example, emissivity is going to change as a function of has it pyrolyzed or hasn't it. So that one's definitely a function of a progress variable, perhaps. And some of these other properties may like, for example, thermal conductivity. So I guess my question is, are we anticipating working with these as fixed scalars, or what sort of accommodation do we want to think about for, like, emissivity as a function of pyrolysis extent, or maybe thermal conductivity as a function of direction through the wood?
Sure.
Some of these
So
properties
that's
may vary as non-scalars.
entirely fair. They may not be fixed values. I think a very broad approach that I'll first say is we don't want to specifically say, here's how you should calibrate your model, or here's what your model should look like. And the level of complexity that is needed there will allow modelers to make that decision. Is it one single heat capacity all the way through? And that's a constant value. Does it change with different components that are reacting? Is there one from my char original wood? Is that temperature dependent? I think you brought up fair points there that they may not be fixed scalars. And so if I can share a new screen, I'm gonna put up the current, what the repo looks like for this wood case. And hopefully that can show a little bit of what we're allowing people to submit and how that might look. So do we see that new window of the MaCFP repo for wood?
Yes.
Yes, that's showing.
Excellent. All right, so in here, we have a folder for our calibration data and templates if you're going to submit cone, TGA, DSC, etc. So if you're submitting that data under different conditions, please follow these templates. In terms of property values themselves and how you submit them, so Morgan may be able to add to this a bit more, but there's a somewhat flexible format that he's developed to allow you to describe each of these property values, how you calibrated them, whether it's this or that tool or manual optimization. And then for each one, do I have multiple reactions? Do I have temperature dependent values for this or that? Are they a single value? Is there going to be a wavelength dependence for this or that property? The hope is to enable people to be flexible in what they submit and how they feel best characterizes the material, but have a framework where you're not just writing this arbitrarily into a Word document, but we have a standard format and the file format and file type that lets you report this in a way that we can directly compare them from group to group. Does that address your question for the most part? Is there follow-up? And then Morgan, do you want to add anything that I missed?
Well, I'll just throw in, it's a really good question. And last time we did it manually, people submitted their models for these different properties and how they varied. Primarily what we dealt with was temperature rather than progress in terms of reaction. But we kind of came up with three forms. People submitted temperature tables, people submitted polynomial functions of temperature, and people submitted power law. And we've come up with a format for expressing that in this JSON file there. There's still some work that probably can be done because there's a million different ways that people can express these dependencies. And I'm still happy. I mean, last time it wasn't that much effort to go through and kind of formalize that information, as you see in this file that Isaac has up. But we will try to share that kind of the ways that we're thinking that you can express these different dependencies. And if you have any other ideas of I don't know, functional forms or other ways to represent material property variation, we're happy to consider them. But yeah, it's a good question and something that's still a work in progress.
Yeah, let me just kind of add in on the kinetics. If you go out into the current literature and look at kinetics for wood pyrolysis, it's not just single activation energy and pre-exponential. A lot of them are, there's a maybe a half dozen. I mean, I haven't looked recently, but a lot of the wood modelers do cellulose, hemicellulose, and lignin separate. A lot of them use multi-step with char steps. I mean, I just kind of see that as maybe getting, there's just a lot more out there in terms of ways that people do it. And so, I mean, I think it's good that we're open here, but I think even if we went to the current literature and just started compiling what they have, we may start running into some roadblocks.
Yeah, Isaac has highlighted there. He did have highlighted kind of our current way of expressing the kinetics, and the one that he's showing has two reactions. It's expressing the reaction order for each of those, the pre-exponential and activation energies for both of those reactions, and other information about the mass fractions. And
those would be serial reactions or parallel.
Yeah, that's an issue. I don't know in this one that he's showing here. We had both. So we handled all of this in the last round of MaCFP. Even with PMMA, people submitted models with two reactions, and so yeah, we allow for that. That table that Isaac showed is really kind of a summary of the classes of properties, I guess, that we're considering, and not precisely how we want people to submit. We're not expecting scalars for all of those things.
Okay.
Stas, I think you had your hand up next, if you'd like to unmute.
Sure. I have a question to Simo regarding the radiation subgroup activities. So my understanding that ultimately we would like to predict radiation from burning fires, and it basically sort of, there are three components to it. One of them, the physical details of the algorithms that are being used, and I think it is my sense, Simo, that you are currently focusing on that part. But there are two other parts, right? One of them is actually optical properties of the species that radiate. And the third one is perhaps an ability to predict the distribution of the species within the flame or hot regions. I guess my question is, do you intend to proceed to look at these two other aspects of the radiative, of ultimate radiative calculations that affect the results, or you intend to constrain yourself to the algorithm side of that problem?
Thank you, Stas. That's a good question. I would say that in this exercise, we are looking at the first two, both the radiation solvers capabilities themselves, but also the gas property models. I would expect that people want to try the performance of gray versus non-gray, radical versus weighted sum of gray gas, and so on, different property models. But up to this point, we have ruled out the we're kind of trying to freeze the scalar fields. That is, we expect that the gas concentrations and soot concentration is as it is, and conditional to those conditions how the radiation models perform, to be able to isolate the sources of error or difference. I noticed that the gas phase group has the goal of looking at influence of soot concentration or soot modeling on the radiation. Now that's already then representing the third step, which you mentioned.
Okay, thank you.
Simon?
Yeah, can you hear me?
Yes.
I had a question which is kind of the continuation of the question from Alex about the input data for the pyrolysis. Could a probably a PDF be an input? Because I know somebody who is working on a pyrolysis with distributed activation energy modeling. And so my question is, could this be acceptable as an input?
Or you unmuted too.
Yeah, don't mean to. Yeah, I mean, I think that information would be great. And we'll receive whatever we can get and try to share it with people as best we can. There is some advantage to providing condensed forms of the information because it allows modelers to use that information readily. If you want to provide a PDF of one of these properties, we can think about ways to formally share that, or at least in terms of a file, of a text file, or a document. And if people want to use that, they can. I don't think we're going to put any limitations on how you present these properties. The key thing is, in that table that Isaac showed, is that those are the things that our current state-of-the-art fire models require. And so we kind of need a complete set of those. If you want to provide that information in whatever form you want, as long as someone can use it in a fire model, then I think we'd be happy to have it. So does that answer your question?
Yeah. Actually, I was thinking we could probably do it in a condensed way by giving the form of the law and just the parameters, so in order not to bloat the data file.
Yeah, and that's a really good point. So if you have like you have a Gaussian distribution for A, you specify that it's Gaussian, and you give the mean and standard deviation, and
yeah, that's enough.
Yeah.
Okay, thank you.
Thanks.
Stas again.
Yeah, I just want to contribute to Morgan's answer. I mean, and it's Morgan and Isaac who work on it, so they seem to be very comfortable with different formats of submitting data and how you represent this models, and this is great. I very much appreciate their ability to accommodate it, and I think they can accommodate it within the GitHub by providing appropriate script. The only challenge that I think everybody who's submitting this property should be addressed is that there should be a pyrolysis model that can take this property as an input, right, without any conversion. So if you're doing a distributed kinetic activation energy model and there is no single pyrolysis model by itself that handles that, then you cannot really couple it with other things, and that means that these properties cannot be used basically in the current form. So keep that in mind, that at the end, at the very least, we would like to be able to solve a problem that involves thermal decomposition kinetics and thermal and mass transport, or at least thermal transport, right? In a best case scenario, you want to provide this data in such a way that this model can also be coupled with a CFD, right? Because ultimately, that's where we're going. We are going eventually to perform flame growth modeling on these materials. It means that your properties have to somehow introduce in the CFD code, and now you're working with within the constraints of pyrolysis models that exist in the fire codes. So I think that the modelers have to be aware of the fact that that's where we're going, and I think we can have an argument of whether it's worth expanding those pyrolysis models in CFD code to include this additional flexibility. But I think we also be well served if we submit it in a form that we can use directly at this point in time.
Yeah, I think that's a really good point. And I think so far with what we've received from MaCFP-3, it wasn't a challenge to because the people who are calibrating these properties are using fire models, and so far it hasn't been a problem to either use directly what they gave us, or it's straightforward to post process what they gave us to transform it into a form that can be used by Thermochem or FDS or fire foam. So, but yeah, you're right, Stas.
Thank you everyone so far for feedback. I'm going to type all these up. We'll include them in the slides when we post them so that others can see them there. Happy to take further questions while we're all still here together. Final chance for questions. Anyone who wants to type something in or share that to the group? Okay, then I will thank you all for coming here. It's been about an hour of your time. We appreciate that focus. We appreciate your 10 years of working with this effort, or if you're just joining us moving forward. If you are interested in joining us for any of these cases, please reach out directly and say, hey, we're with this group. We'd love to be part of the effort. We can run these tests. We can do this modeling. We're absolutely happy to have you there with us. The kind of core meeting part of all of this is our GitHub repo. So please check that, follow that for updates. And if you have follow-up questions, you can send that to me or any of the community members directly, or post that to the whole community as an open thread to see how we can work together on that one. So thanks for being here, and we'll post a recording of this in the next few days. And that's really all I have. If committee members can stay for a few minutes, it might be nice to catch up just before, while we're all here together. But everyone else, have a wonderful day.
Thank you. Bye-bye.
Thank you.
Thank you, Isaac.
Thank you, Isaac.
Let me at least stop recording. It's gotta be